So, quick review from Friday. Okay, we were talking about the laws of thermodynamics on Friday. Okay, and the first law of thermodynamics was essentially the law of conservation of energy. Okay, and that is that energy can't be created and it can't be destroyed. It can be turned into other forms. Okay, like heat, like sound, okay, from potential to kinetic, all of that can happen, but it can never go away entirely, right? We talked about the second law of thermodynamics that says that energy flows from hot to cold, okay? And we talked about the three kinds of systems: open, closed, and isolated. An open system can exchange matter and energy with its surroundings. So basically, you are an open system in this room right now, okay, the room being your surroundings. A closed system can exchange only energy, not matter. So it would be something that is sealed airtight, but not insulated. Okay? And then there is an isolated system, which is purely theoretical, okay, and supposedly cannot exchange either matter nor energy with its surroundings. Okay? Then we got into this whole thing about the second law of thermodynamics, energy going from hot to cold. Okay, we talked about the weird design for that boat, okay, that had the long pipe, okay, that went down into the water, and the idea being that the warm water at the surface would run through the engine, through the turbine, and down into the cold water through the really long pipe, which we said was completely unrealistic because those waters are already in contact with each other, okay, and there wouldn't be a huge temperature differential. But the idea is sound, okay, and we talked about this using the second law of thermodynamics, okay, this little like hot water heater that could heat water in a hot tub, okay, so the cold water would come in. So the cold water would come in through this pipe, okay, go into the water heater and be heated up, come out through the pipe at the top and go into the tub, and that would create a current or a convection current where that energy would be exchanged, okay, and it would keep going through because of the second law. Okay, the second law is going to keep that water flowing through that heater, okay, until such time as everything is the same temperature, and then it'll stop. Okay, if it goes faster, the greater the difference in temperature. So that is the principle behind heat engines. Okay? Heat engines use the second law of thermodynamics. If there is a really hot area and a really cold area, energy will want to flow from hot to cold. When it does so, it usually will take matter with it. Okay? That movement of matter can then be used to turn a turbine or something else, okay, to generate power. Right? That's the principle behind a heat engine, and that is exactly how a jet engine works. Okay. In a jet engine, you've got the area of combustion, okay, near the front of the engine. Air goes through the engine, okay, transferring that heat out to the back, and that spins the turbine that creates the thrust, okay, from the jet engine. The greater that temperature difference, the faster the turbine will spin, and the more thrust will be produced. If there's an afterburner, there's a second, basically hot spot, okay, that is continuing that and creating even more thrust. Okay. Does that make sense? A heat pump works the opposite way. Okay, so a heat engine uses the second law of thermodynamics. A heat pump goes against the second law of thermodynamics. So if the jet engine is diffusion, the natural flow from high to low, a heat pump is active transport. It uses energy to actually pump hot air or hot water from the hot area to the cold area. Okay? Since you're going against the direction it wants to flow, you have to put energy into it. Right? This is how an air conditioner and a refrigerator work. And so an air conditioner and a refrigerator are both heat pumps. They take the air from inside your house. Okay? I said that backwards, didn't I? I said from the hot to the cold, didn't I? From the cold to the hot is the other way. Okay, so with an air conditioner, what it does, it takes the air in your house, which is not as hot as the air outside, and it runs it through the air conditioner, which contains a compressor and a condenser, okay, and it cools it. And then it pumps the heat using a fan to the outside air, which is already hotter. Okay? It uses a lot of energy. Your fridge and your air conditioner are the two largest consumers of electricity in your home. Okay? It takes a lot of energy to pump heat in the other direction. Okay, because the second law of thermodynamics wants it to go from hot to cold, and your air conditioner or refrigerator is pumping it the other direction. Okay, your fridge works exactly the same. Running down the sides and back of your fridge are coils. Okay, your air conditioner has coils as well. Okay, and these coils contain coolant. The coolant changes state from liquid to gas around the temperature of your refrigerator and freezer. Okay? And so as it absorbs energy from the food inside the fridge, it changes state from liquid to gas. That takes a lot of energy. Okay? Then this gas goes back down to the compressor. Okay? So you got these coils, okay, and they're going to take that coolant down to the compressor. So the hot coolant is going to run from the coils to the compressor. And what do you suppose the compressor does to it? Kind of like its name would imply. What does a compressor do? Compresses things, exactly. And when you put a gas under pressure, or you compress a gas, you can turn it back into a liquid. When you do that, it releases all of the energy it absorbed to become a gas. Okay? So when that energy is released, because it's changed back into a liquid, it is blown out the bottom of the fridge by the fan. You may have noticed that there's usually warm air coming out from under the bottom of your fridge when it's running. Okay? That warm air, that heat, is coming from the food inside the fridge. Okay? It's pumping it out into the hotter area, because obviously it's hotter in your house than it is inside the fridge. So it's taking heat from a colder area and pumping it out into the hotter area. Okay? Does that sort of make sense to everybody? All right, so can you air condition your house with your fridge door open? Why not? You're right, you can't. Why not? Homer Simpson tried it once. Where is it trying to pump the cold air? Or the hot air, sorry. It's trying to pump the hot air back into the house. So if you just leave the door on the refrigerator open, what's the refrigerator going to do? It's just going to run continuously. Okay? Because as it pumps air from inside the fridge to the surroundings go back into the fridge. Okay? And it can never get ahead. It just keeps running and running and running. It was never designed to cool the volume of air that is your house. And your air conditioner is designed to do that, but your refrigerator is designed to, well, cool about, what, 24 cubic feet? Okay? If you got a really big fridge, okay, of air, not your whole house. Does that sort of make sense to everybody? How heat pump works. Okay, realize guys, I'm getting zero interaction from you, and I'm just going to start picking people. So if you know the answer, volunteer. Otherwise, you risk getting picked. Okay? I'm just kind of tired of being the only guy who's doing it. Some contribution from you guys, or I feel like you're not paying attention. Okay? Got to be active learners here. All right, so if we go back to this idea of the heat engine, one of the earliest heat engines was actually something like this. Okay? And they just put an electric motor on and used essentially a thermocouple. They had hot water in this beaker, 90 degrees Celsius, cold water in this beaker, 10 degrees Celsius, and they had basically copper plates attached to this electric motor with a fan on it. Okay? Because there was a lot more heat in the 90, this copper plate heated up more, okay, and energy ran into the electric motor and then up to the 10 degree. Now what do you suppose eventually happened with these two beakers?
They balance off.
Yeah, eventually they balance off. What happens to the speed of that fan as they get closer and closer to each other's temperature?
It slows down.
It slows down, yeah. The greater the difference, the faster the rate of transfer. So if there's not much of a difference, then you don't get that fan spinning very quickly. Thank you, I appreciate that for contribution. Okay, does that sort of make sense? Yeah. So, for a heat pump, okay, remember that in a heat pump, the process is not natural. Okay, energy wants to flow from hot to cold. A heat pump is making it go the other way. Right, that requires energy. So we put a lot of energy into that, okay, in order to make it happen. Okay, thermal energy is then transferred to the air surrounding the refrigerator, the hotter surroundings, okay, and the refrigerant is pumped back to the condenser, okay, or the compressor, cooled and liquefied, and then recycled. Okay, So the compressor is the loud thing you can hear running, okay, when your refrigerator is running. Okay? It doesn't run all the time unless you've left the fridge door open. Okay? But when you close the fridge door, the light goes off. It does. There's no way to check that, but it goes off. Okay? And the compressor won't run as much. Okay? All right, everybody good with those ideas? Okay. I would like you guys to answer those questions. Okay, complete sentences, okay, do a good job of it, kind of thing that could end up on a quiz like tomorrow. Something like that. Okay, let's have a look at these ones here. So, question number 2. First law of thermodynamics says that energy cannot be created, it cannot be destroyed, it can be transferred, it can be converted. Okay? When work is done to a system, it gains mechanical energy. When work is done by a system, it loses mechanical energy. If heat is transferred to a system, it gains thermal energy. If heat is transferred away from a system, it loses thermal energy. That's the very extended version, okay, of the first law of thermodynamics. Okay, what is the distinction between work and heat? First thing, work and heat are both transfers of energy. Okay, so they have that in common. They are both transfers of energy. It's the type of energy they transfer that is different. Work transfers mechanical energy, where heat transfers thermal energy. Okay, that's the distinction between them. The type of energy they transfer is different. Work is mechanical, heat is thermal. Okay, identify whether each of the following is best explained by the first or second law of thermodynamics. A bouncing ball eventually comes to rest on the floor. Which law best explains that?
The first law.
First law? So energy can't be created or destroyed, but the energy is being transferred away. Okay, I can go with that. I would have thought second law myself because it's mostly about the transfer of energy away, but it is at least accounting for the fact. The first law does account for the fact that energy is conserved, but in this one, because it eventually comes to rest, we know that it's losing energy to its surroundings. The ball itself isn't keeping the energy. Okay? If it said a ball bounces back and forth, up and down to the same height every time, then I'd say absolutely 100% only the first law. Okay? But in this case, I'd say a little bit of the first law as long as we account for the fact that the energy is being lost or being converted, okay, to the surroundings, and a bit of the second law because we have to acknowledge that it is in fact going to the surroundings as heat and sound and other things. Okay? A metal spoon eventually becomes hot when placed in a pot of boiling water.
That's the second law.
Definitely the second law. Heat flows from hot to cold. Okay? It's why we typically don't use metal spoons if we're going to keep them in the pot for very long. Okay? Because they do tend to conduct heat very well. Okay, energy cannot be created or cannot be destroyed. I wonder. Okay. Second law of thermodynamics for question number 7. Energy always flows from high to low, hot to cold. Okay, something like that. Okay, number 9 is one you need to think about. Water is observed to condense on the outside of a cold glass. Which way is energy, or is heat flowing? Is it flowing from the surroundings into the glass, or the other way? Into the glass. The glass is colder, first off, so we know the second law says energy has to be going to the glass, but here's why the water condenses on the outside. Okay? When water condenses, it actually loses energy to its surroundings. Okay? Because water vapor has way more energy than liquid water does. So when you see water vapor condense and turn into a liquid, it's actually transferring a great deal of water, or sorry, not water, energy to whatever it condensed on. right? That's why your drink, your cold drink, doesn't stay cold. Okay? It's going to very rapidly gain energy from its surroundings, either just from energy flowing in or from water vapor condensing on the outside of it. Okay? Have you ever heard this? Be careful, steam burns you worse than boiling water. Well, it's exactly that reason. Steam, even if I have steam at 100 degrees and I have water at 100 degrees, the steam is still way worse. Okay? It has way more energy because not only is it 100 degrees Celsius, but it's already changed state from liquid to gas. And for water, that takes, what was it, forgetting how much now, but it's a huge amount of energy, 2,200 and something joules for every gram of water. Okay, so steam holds way more energy than water does, even if they're the same temperature, because steam is in its gaseous state, which is a higher energy state than liquid water. Okay, so if you get steam on your arm from like a tea kettle or a broken pipe or something like that, and it hits your arm, it's going to burn you a lot worse than if you were sprayed with liquid water. Okay? Because first off, it's going to condense back into a liquid and release all of that energy. And then it's also still 100 degrees Celsius, and that's bad. Okay? So it gets you kind of twice, whereas water only gets you once. Okay? So there's energy flowing definitely into the glass for that reason. Okay? This is also why sweat works the way it does. Okay? If you work out and you get all sweaty, okay, and then you walk outside, you feel cold. Okay? Because the water is evaporating from your body. Okay? And to evaporate, water has to take energy, and it takes it from your body. Okay? 2,260 joules for every gram. Okay? It's over. Does that sort of make sense? All right, and then which law of thermodynamics best describes the following statements? You can't get something for nothing. Yeah, first law. Definitely. Can't get, I mean, energy can't be created. There you go. Can't get something for nothing. Okay? You can't even get close. I think they're supposed to mean you can't even get close to getting something for nothing. Still first law. I'd say also second law thrown in there because that's kind of that whole perpetual motion machine thing. Okay? And a rock will never suddenly jump into the air. Still the first law. Okay, that would require you to create energy. Okay, rocks are not living things. Okay, they just sit there. Right? They're not going to jump into the air. If they do, well, it's a whole new world. Okay, and kind of a scary one because rocks apparently jump into the air in that world. Okay. All right, everybody good with those? Okay, now this, I can't remember if I actually put this in your notes package or not, but it's just something we're going to talk about because it's kind of applications of thermodynamics. Okay. The design of machines, engines, and tools took kind of a weird path. Okay? We started building machines and tools before we really understood the science behind them. Okay? We needed things, technology to do a job. That's what technology is, applied science. It's science applied to do a job. But sometimes our technology gets ahead of our understanding. And the building of engines is kind of a prime example of that. We didn't always understand exactly how the laws of thermodynamics applied to this stuff, but we did it because we could. Okay? So some of the earliest machines were things like the Archimedes screw. Okay? The Archimedes screw was the first pump. It was great for moving water from low areas to high areas because obviously water doesn't do that on its own. Water flows downhill according to the second law of thermodynamics. Okay? So the Archimedes screw is basically, well, like any other screw. It's an inclined plane wrapped around an axis. So if I ever tell you that you're an inclined plane wrapped around an axis, it means you are screwed. Just so you know, that's Sheldon Cooper to it. I can't take credit for that. Okay? So it's an inclined plane, but it's wrapped around an axis. So if you can spin it fast, the polar nature of water will have that cohesion and adhesion, have it stick to the blade, okay, and it'll go up. Now this only works, for a couple of meters. You can only spin one of these so fast. okay? And obviously gravity will start pulling that water down against those hydrogen bonds. They're not that strong, okay? So it was good for the time, but it's not like something we would use today, okay? There's also things like the Persian wheel, okay? Which you could take, you had one wheel that spun the other wheel, and this wheel had buckets on it, okay? And so you could raise the water out of there and drop it onto this, and then an aqueduct system would carry it somewhere else. Okay, the Persians were big for building aqueducts and things like that. Okay? Now, this was all powered by either people or livestock. Okay? We didn't really get into true engines until we started making them use fuel. Okay? So the first fuel was, or the first engine kind of powered by fuel was like Hero's steam engine. Right, which used, you burned coal, you evaporated water, turned it into steam, and steam could flow pressurized through something and turn something else. Okay, turn something, make it work, okay, move a piston up and down, okay, things like that. All right, so we started building these engines, okay, not really understanding how it all worked. Okay, more modern pumps, like instead of the Persian wheel and the Archimedes screw, okay, are reciprocating pumps. Okay, the screw and the wheel, they didn't do much, they just kind of turned. Okay, but a reciprocating pump actually pumps in both directions. So there's a two-way valve system here. Okay, sorry, one-way valve system. As you pull this piston back with the crank, it creates a suction. That suction will bring the top valve down and the bottom valve up, which will draw water into the pump chamber. When the piston starts going this way, the pressure closes this valve, pushes this valve open, and shoots the water through that valve upwards. So it's actually doing work in both directions. Okay? Once that was kind of figured out, then we could attach a motor to it to make it do that instead of having a person or a horse or whatever actually doing the cranking. Okay? So if you remember before, we talked about these hidden secrets that were in some of the fuels that we used, that wood could make so much energy, but coal made more, and so on. Okay, well, that's what engine technology kind of came from. Okay, so the first engine, okay, was built, or not actually built, it was designed by Christian Huygens. Okay, that's also the guy who was the probe that landed on Titan was named after him. Okay, he did some stuff with astronomy as well. Okay, but he was a Dutch mathematician, and he recognized that this reciprocating pump needed something that could power it, so it wasn't connected to a person or an animal. Okay, so he said, I'm going to build an engine that can use the pressure of an expanding gas to do work. Okay, he knew that's what steam could do that. So he thought there's got to be a way to use expanding gases to push a piston that can be connected to this crank, which is basically how all engines today work. So he designed the gunpowder engine. Now, as it would sound, it was pretty dangerous. So thus it was never actually, there was no actual prototype ever built or tested. But the idea is sound. If you blow up gunpowder, it explodes. And an explosion is rapidly expanding gases. And they can do work, also known as destruction. Okay? It's that pressure wave of the explosion that does all the damage. So he said, if I can contain that in a small space, then it can do work. This is how a cannon works, right? Like if I detonate gunpowder and I have a ball there, the expanding gases push the ball up. Well, if I replace a ball with a piston, the piston can do work. The problem being, you're containing an explosion. What's the problem with containing an explosion? Explosions don't like to be contained. That's the problem with containing an explosion. Okay? You really have to control that explosion. Otherwise, it just explodes, and then it's bad. Okay? So the gunpowder engine was never actually built, okay, but was, sound in its design, at least. Okay? One of the earliest steam engines, okay, looked something like this. Now, what we use today are called internal combustion engines because the explosion or the combustion happens inside the motor itself, okay, right next to the piston. This is an external combustion engine. the steam and the water and the piston are in a separate chamber from the heat source. Okay, so this first engine was not efficient at all. They would start the fire, which would boil the water, and the water would turn into steam, and the steam would slowly lift the piston, which could then be attached to a crank or a cable or something and do useful work. Once you got the piston to the top of the chamber, you had to spray water all over this thing in order to do what? Once the piston gets to the top, can you get anything else out of this? No. That's as far as the piston can go. You need the piston to come back down. So you spray water all over this, which puts out the fire. Okay, cools it down, the steam condenses back into water, and the piston goes back down. Then you light the whole thing back up again, and you get the piston to go back up. Is this very efficient? Terrible. Okay, terrible. But it was early. Okay? It was the early designs of engines and things like that. Okay? The idea was sound, still worked. You could use steam and expanding gas that didn't blow up in your face to do work. Okay? All right. So once people realized that, the design of steam engines kind of rapidly improved. There was kind of very quick development or evolution of the steam engine. But they all were external combustion. You had essentially a boiler, okay, where the water was, and the steam was produced, and then you had the heat source, usually a coal-fired furnace underneath it. Okay, and so you get your steam in here. The steam would, do its work. Okay, make things go, and then it could be brought back to the boiler after it condensed. So there could be some circulation, okay, things like that. Or fresh water brought in, okay, hot water out, whatever. You get the work done that way. Okay. With this one here, okay, same idea, which we're getting more efficient. Instead of having the fire being completely open, we had an enclosed furnace, okay, things like that. So they got kind of more and more efficient, used less and less fuel, okay, and were able to reciprocate much more. Okay, Watt is the one who probably developed the best, okay, one of the best steam engines. Okay, so he was actually asked to repair an older model, and he couldn't believe how bad it was, okay, how poorly it performed. He realized there was a tremendous waste of heat when the water was heated and cooled in the same cylinder. Okay, so Watt designed a new, more efficient steam engine that had a separate condenser to condense the steam, so that the boiler cylinder always remained hot, which makes good sense, right? Why would you cool your main boiler every time you needed to move the piston? So that reduced the amount of heat required to operate it, okay, made it 3 times more efficient, okay, and Watt's steam engine was used for a very, very long time. So this is kind of what our timeline looked like, okay. So less than, around 100 years or so, we go from kind of the earliest designs of engines to basically the internal combustion engine, which came around 1890. Okay. Now, the internal combustion engine was kind of it basically fueled most of the 20th century, okay, and obviously still today. So the idea here was that you had to have a fuel that you could burn inside the cylinder, and you didn't need water then. Okay, so this wasn't a steam engine anymore. This was fired by some sort of liquid fuel or a fuel vapor. So the first ones, they weren't terribly efficient. They used like coal oil and tar and stuff like that. They would get gummed up really badly. Okay, you had to get the spark was always going out, and you always had problems with it. They would seize if they weren't properly lubricated. Okay, they were just not very efficient. Okay, but then, okay, Otto and Longen designed what is essentially called now the 4-stroke internal combustion engine. Okay? There's basically 2 kinds of combustion engines, 2-stroke and 4-stroke. Okay? A 2-stroke engine would be what you would have on a weed eater, okay? A chainsaw, okay? Like a post hole auger, an ice auger, something small. 2-stroke engines, motorcycles sometimes, like really, like dirt bikes will sometimes have a 2-stroke engine. In a 2-stroke engine, you actually mix the fuel and the oil together. Okay, so there's not a separate thing of oil. And so as the fuel goes in, the oil goes in with it, and it lubricates the cylinder, okay, as the fuel is burned. They're pretty dirty. That's the drawback to them. They work really well, but they pollute a lot because they're constantly burning the oil. Okay? In a four-stroke engine, you get one power stroke out of 4 strokes. Okay, so there's 4 strokes in a 4-stroke engine, hence the name. Right? So what happens in your car, okay, is that you start out with the intake stroke. In the intake stroke, the piston is moving downwards. Okay? And what happens is when it goes downwards, your cam, which changes your valves or moves your valves, opens the intake valve and closes the exhaust valve. This draws in the air-fuel mixture, okay, which in a fuel injection motor, which is what most of us have, okay, is going to actually be actively injected into the cylinder, okay, and this is mostly going to take in air. Okay, so air is coming in. Okay, the next stroke is the compression stroke. So now the piston is going to start moving upwards, and both valves are closed. And what that's going to do is it's going to put the air-fuel mixture under pressure. Okay, that's going to make it burn hotter. Okay, if it's not compressed when it ignites, it doesn't produce nearly as much power. Okay, so you've got the piston moving up and compressing the gases. Right? Then you have ignition. That's not a separate stroke. Okay, that's just what happens at the top of the compression stroke. Okay, so when the spark plug fires, it's just an electric spark. Okay, it ignites the air-fuel mixture, and that blows up. It's a small explosion every single time, and this happens thousands of times per minute in each cylinder in your motor. Okay, so there's these little explosions that happen, okay, and that causes the expansion, or what we call the power stroke. Okay, so the gases explode and they push the piston down. Okay, that's the only stroke where actual work gets done in the motor. The rest are just for moving gases around. So now, once that thing gets to the bottom, once the piston gets to the bottom, then we have the exhaust stroke. Okay, and that is that the piston now moves up, the intake valve is closed, the exhaust valve opens, and your spent gases, carbon dioxide and water vapor, go out to your exhaust system and out the tailpipe. Okay, that sort of makes sense? Okay. That took a lot of design to come up with that idea. Now that is, of course, greatly simplified. Okay, that's just talking about what goes on in the actual cylinder of one of your cylinders in your car. Okay, there's a lot more that goes into that, delivering fuel and mixing it and all of that kind of stuff. But that's generally how an internal combustion engine works, and it makes it much more efficient than like a steam engine or something like that. Okay. Now, when you ignite gas, you obviously get the expanding gases, and that's a little bit of heat, but it's mostly just that the gases produced take up more space. So how much of the energy that's in the fuel do you suppose actually moves the car? Actually does useful work? Because what is there a lot of produced here that's not doing any mechanical work? Heat, yeah. Okay. In a modern, let's say, sedan, okay, not an SUV, maybe a small SUV, but a modern sedan, 4-door car, the engine will run at around 20 to 22% efficiency. Okay, and that's it. If you have a hybrid car, that efficiency goes up a bit. Okay? If you have an electric car, it's far more efficient, but it doesn't use, obviously, internal combustion. Okay? But an internal combustion engine loses the vast majority of the energy and fuel to heat. I mean, the gases coming out of your exhaust pipe are really hot. Okay? That hasn't really done a lot of useful work. In fact, your car uses a bunch of the energy that it gets from the fuel to keep itself from melting down. Okay? Your cooling system, the water pump and the radiator, okay, that circulate coolant through the car, okay, they're there because without them, the car would literally melt down. Okay? It produces so much heat that doesn't do anything useful that there actually has to be a system that vents the heat away. So it's not super efficient, but it's obviously way more efficient than a steam engine and doesn't require you to carry a whole bunch of coal and a whole bunch of water around. Okay, because that's kind of inefficient too. Okay, so that's not something that we're ever gonna have on a test. I just always go over it because people ask kind of how that stuff works, so that's how that stuff works. Okay. Let's say it's lunch and you're gonna walk to 7-Eleven to get something. Okay? So we start here at the school. Okay, you walk down 32nd Street, okay, to to 7-Eleven. Okay? How far do you think it is to walk to 7-Eleven?
Maybe just under a kilometer.
Yeah, I'd say it's probably like 800-900 meters. Let me Google it. Let me put it in Google Maps and see how far it is from here to 7-Eleven. Yeah, we'll say for right now it's like 800 meters, but I'm actually now morbidly curious to find out just how far. Maybe I'll do it.